Hello, I'm Sapna Davis of ECE Department, Rajagiri School of Engineering and Technology. Discriminant functions and decision surfaces. A classifier can be defined in terms of a set of discriminant functions GIX, where I varies from 1 to C, where C is the number of classes. The classifier assigns a feature vector x to the class omega I if Gi of x is greater than Gj of x for all j not equal to I. So classifier is a machine that computes C discriminant functions and selects the class corresponding to the largest discriminant which is shown in the figure. So here x1, x2 to xd is the d-dimensional input vector. Then the classifier will be computing g1x, g2x up to gcx, and based on the value of the discriminant function, the action or the classification will be performed. Let Gix equal to minus r of alpha I on x, then maximum discriminant function corresponds to the minimum conditional risk. For minimum error rate, Gix equal to p of omega I on x, then maximum discriminant function corresponds to the maximum posteriori probability. The choice of discriminant functions is not unique. If we replace Gix by f of Gix, where f is a monotonically increasing function, the classification remains unchanged. Let Gix equal to p of omega I on x, which can be replaced in terms of the likelihood probability and the priori probability. The denominator here is a px, which is just a scale factor. Hence, Gix equal to p of x on omega I times p of omega I. We can take the logarithm of this equation. Then Gix will be equal to logarithm of p of x on omega I plus logarithm of p of omega I. Any decision rule divides a feature space into C regions R1 to Rc. If Gix is greater than Gjx for all j not equal to I, then x is in Ri and the decision rule assigns x to omega I. The regions are separated by decision boundaries which are surfaces in the feature space. In the figure, you can see two discriminant functions and accordingly there are two regions R1 and R2. The decision boundary between R1 and R2 is also shown in the figure. Consider the two category case. Here the classification can be done by defining two discriminant functions G1 and G2 and assign x to omega 1 if G1 greater than G2. Instead, we can define a single discriminant function gx where gx equal to g1x minus g2x. Then the decision rule will be decide omega 1 if gx greater than 0, otherwise decide omega 2. Gx will be equal to p of omega 1 on x minus p of omega 2 on x, replacing the posteriori probabilities in terms of the likelihood probabilities and priori probabilities and taking the logarithm, we can rewrite the Gx equation. The Gaussian density function is given. Univariate means the variable x is a single dimensional, mu is the mean and sigma is the standard deviation. Here the multivariate Gaussian density function is given. Multivariate means the variable x is a multi-dimensional. So x is the d-dimensional vector, mu is the d-dimensional mean vector and sigma is the covariance matrix. Next is the discriminant functions for the normal density. The minimum error rate classification can be done using discriminant functions Gix equal to log p of x on omega I plus log p of omega I. Now p of x on omega can be replaced with the multivariate Gaussian density function and Gix can be obtained. Now consider the case sigma I equal to sigma square I. This occurs when the features are statistically independent and each feature has the same variance sigma square. In this case, the covariance matrix is diagonal. Determinant sigma I equals sigma raised to 2d and sigma I inverse equals 1 by sigma square I. Since the second and third term in Gix equation are independent of I, they can be ignored. Then we get the Gix equation. Then expand the quadratic term. Now in the Gix equation, x transpose x is same for all I, so it can be ignored. Hence, we get a GIX equal to WI transpose X plus WI0. WI and WI0 equations are given. WI0 is called as the bias in the ith direction. A classifier using linear discriminant functions is called a linear machine. The decision surfaces for a linear machine are hyperplanes defined by the linear equations GIX equal to GJX for the two categories. This equation can be written as a GIX minus GJX equal to 0. Replace for GIX and GJX. Finally, we get W transpose X minus X0 equal to 0. This equation defines a hyperplane through the point x0 and orthogonal to the vector w. If P of omega I are the same for all C classes, then log P of omega I in GIX equation can be ignored. Then the optimum decision rule will be to classify a feature vector x, measure the Euclidean distance x minus mu I from x to each of the C mean vectors and assign x to the category of the nearest mean. Such a classifier is called a minimum distance classifier. Second case, the covariance matrices of all classes are identical but arbitrary. Since both the determinant sigma I and the d by 2 log 2 pi term in GIX equation are independent of I, they can be ignored. Then we get the GIX equation. If P of omega I are same for all the C classes, then log P of omega I also can be ignored. Then the optimal decision rule is to classify a feature vector x, measure the squared Mahalanobis distance x minus mu I transpose sigma inverse x minus mu I from x to each of the C mean vectors and assign x to the category of the nearest mean. Expansion of a x minus mu I transpose sigma inverse x minus mu I results in a term x transpose sigma inverse x which is independent of I and can be dropped. The resulting discriminant functions are again linear. GIX equal to WI transpose x plus WI0. Since the discriminants are linear, the resulting decision boundaries are again hyperplanes. If Ri and Rj are contiguous, the boundary between them has the equation W transpose x minus x0 equal to 0. Third case, the covariance matrices are different for each category, then only d by 2 log 2 term can be dropped in GIX, resulting in a quadratic equation for GIX. The decision surfaces are hyperquadrics and can assume any of the general forms like hyperplanes, pairs of hyperplanes, hyperspheres, hyperellipsoids or hyperparaboloids.